Now that you have your medical degree, you decide to hang a shingle, also known as a sign, in front of your home and begin your practice. The figure shows a flagpole, if you will, held up with a wire attached to the right-hand edge and bolted on the left to the wall of your home. A, what is the tension in the wire? B, what is the normal force from the wall? And C, what is the upward force from the wall? The characteristic that identifies what kind of problem we're dealing with is that everything in this problem is motionless, meaning we have an equilibrium problem. Equilibrium problems are force problems, and the first step in every force problem is to draw a free body diagram. I'm selecting the flagpole to draw because this object experiences more forces than anything else in the diagram and will be the appropriate one for the analysis. The first force we identify acting on the flagpole is gravity. Gravity acts at the midpoint of the flagpole and is of an amount m times g. The next thing we notice is the sign itself. This sign is located 80% of the way from the left to the right of the flagpole, and we will place its force vector at that location, 80% of the way from the left towards the right, and this force vector is of course of an amount m of 12 kilograms times g. Next we notice the wire that is holding up the right-hand edge of the flagpole. The wire creates a tension, and as always, tensions pull, and they pull in a direction along the wire or string, meaning that the tension force goes this way at an angle of 35 degrees as indicated in the figure. Finally, we need to deal with the wall. You might think that the wall should be dealt with as a contact force because it's a surface against which the flagpole rests. Well, typically with a contact force, we refer to an object that is resting but not attached. Here, we think it would be awfully foolish to rely on friction to hold up the flagpole. You will most likely bolt, nail, or in some other way attach the left-hand edge of the flagpole to the wall. This means that the wall will be capable of generating a force in any possible direction. However, looking at parts B and C closely, we've been given a hint to assist in solving the problem. We've been told that we should break the force of the wall into two components, the first one of which is normal or perpendicular to the wall, and the second of which will be upward. Why upward? Well, imagine that you pressed it downward on the left-hand edge of the flagpole. It would certainly fall. Upward is the necessary direction to keep the flagpole off the ground. Now that our free body diagram has indications for every relevant force in the problem, we need to select a coordinate system. Since the object is not accelerating, we won't use that to denote the direction of the coordinate system, but we will use the principle that we want to make the equations that come from this free body diagram as simple as possible. We notice that of the 5 forces in this free body diagram, 4 of them lie nicely along a Cartesian coordinate system with horizontal and vertical as the 2 relevant axes. That's the coordinate system that we'll use for this problem, and because of this, only one of our 5 forces will need to be broken into components. That one is the tension force, and we'll proceed to do so now. We begin by starting at the base of the tension force and following one of the axes, this is the horizontal, until such time as completing the triangle is parallel to the other axis, which is vertical. Since the angle between the wire and the flagpole has been labeled as 35 degrees, we can recognize the 2 components of the tension. This one here is opposite to the 35 degrees and is therefore tension times the sine of 35 degrees. And this one over here is adjacent to the 35 degrees, meaning it is of an amount tension times the cosine of 35. We're now ready to formulate the equations that come from this free body diagram. One of them will be in the x direction, another one in the y direction, and then finally we'll need to formulate a torque equation around some axis. In the x direction, there are only 2 forces. One of them is the normal force, and the other is one of the 2 components of the tension. We'll take right to be the positive direction, meaning that normal will come in with a plus sign, and tension cosine 35 will come in with a minus sign. Since there's no acceleration in any direction, the forces sum to 0. This equation has two unknowns, and therefore we will place it in a box to save it for later. Next is an analysis of the y direction. We will call up positive for y, in which case there are two up and two down forces. The up force are the ones we labeled U for the upward force due to the wall, and also the component of tension, which is opposite to the 35 degrees and therefore is sine of 35. The two downward forces are 6g and 12g, and as previously, the sum of all forces is 0 since there's no acceleration. Among these two equations now, we have three unknowns, and so we place another box, since we require one more equation to get the full solution. The third equation will be a torque equation, and we recognize that the sum of the torques will be 0 since the object has no angular acceleration, but we must ask ourselves an interesting question. Since every torque requires that we multiply the force times radius, where radius is the distance between where the force is applied and the pivot point, around which pivot point is the object not rotating? That's actually a trick question. The reason is the object is not rotating around any axis you wish to name. I've drawn the blue dot at the left-hand edge, and surely this flagpole is not rotating around the left-hand edge. Neither is it rotating around the center, nor is it rotating around the right-hand edge, nor is it rotating around the place where the flag hangs from, nor is it rotating around an arbitrary point located over there. This flagpole simply isn't rotating. Because we have a freedom in selecting which is the pivot point around which we are not rotating, we can choose to make the equation as simple as possible by placing this pivot point cleverly. If we were to place the pivot point on top of one of the known forces, for example here, the 6g would not appear in our equation, but that doesn't buy us much because leaving a known out of an equation isn't so helpful. There are two reasonable locations at which we would like to place this point. One of them would be here, such that neither the upward nor the normal force would appear in the equation, and the other would be on the right-hand edge, in an attempt to eliminate the tension from the equation. I'm going to place this point on the left-hand edge and then proceed to formulate the clockwise equation. We've chosen the clockwise direction arbitrarily to be plus. You could have chosen counterclockwise and still get the answer correct. Formulating the equation, we ask ourselves which forces lead to torques in the positive or clockwise direction. The first one is the gravity acting upon the flagpole itself. That force is of an amount, 6 times g, but this quantity as written is merely a force. It is not a torque. We need to multiply any force times the appropriate radius in order to get this to be a torque. Since the 6g is applied at the midpoint of the flagpole, the distance from the pivot to this force is half, or 0.5, times the length of the flagpole. The next force that contributes a torque, tending to move the object clockwise around the given pivot, is the weight of the flag or sign itself. This is 12g for the amount of force, and we again need to multiply force times radius in order to make a torque. The radius will be 0.8 times the length of the flagpole, and so this is the correct term for the torque due to the weight of the flag. We only have one more term to go, and that's going to be the negative term due to the tension. Looking at the diagram, we realize that we must be careful when determining the force due to the tension. The reason is any force that is directed straight towards or straight away from the pivot does not contribute to the overall torque. Notice that we have broken the tension already into two components, the tension times sine 35 and the tension times cos 35. The tension times cos 35 is a force that is pointed directly towards the pivot and does not tend to turn the flagpole either clockwise or counterclockwise. For this reason, only the piece of tension tension times sine of 35 contributes to making a torque. And so this is what we write in our equation. This is the correct amount of force using only the component perpendicular to the radius vector. However, it's still not a torque until we multiply it by the appropriate radius. Since the wire is attached to the far right-hand edge of the flagpole, it is a radius of L, completing our torque equation where the torques sum to 0. Please notice two things. Number one, since there is an L in every term, we can factor that out and divide it away. And number two, the only unknown in this problem is the tension. Therefore, we will be able to solve for the tension directly, yielding the numerical result 215 newtons. This result can be placed into each of our prior two equations for both the x direction and for the y direction, and that will yield the values of the normal force as well as the value of the upward force. Starting with the x equation, we notice that the normal force will be equal to the tension times the cosine of 35 degrees, yielding the numerical result 176 newtons. The same consideration in the y direction tells us that the upward force will be equal to 18g minus the tension times the sine of 35, leading to the numerical result 52.9 newtons.